Swayam Prabha. Digital India. Educated India.
Okay, hi. So we continue on the course following Sagar's presentation. What I'm going to tell you is on following up from his presentation and my presentation. Now, one of the points that you will be hearing during this course is about in situ studies and about operando studies. So to some extent, this is also important to draw a line what we understand by in situ, what we understand by operando, and why we have two words that are apparently similar, but they're actually not similar. So basically what I have is a parallelism between what could be representative of the idea about in situ. I mean, in situ, in general, it comes from Latin on-site, so that the sample is on-site, and then you do some treatment of the sample on-site, and when it is on that site, the in situ cell, you go to the spectrometer, you measure, and you read the results. So on-site only means that it is on the site. And in the case of operando, comes from Latin operando, which means working, you know that this sample is actually working. So somehow this is like when you go to an office and people check in and check out. And in between, the people is working, probably. But you don't know. It's like they're on site, they are in situ, but you don't really know what is happening there. On the other side, with the operando approach, you are assessing the people on performance. So you do see that they are working, you do see what they are doing. And that is like the key difference, that in the case of operando, you not only characterize under a given environment on the site where you have, but this site is actually the working place, and it is in actually working conditions, and you are measuring this performance. We will come into operando, not today. Today we will have more in situ things and characterization things, but that is the key idea. Also a little bit of grammar, because sometimes I got into philosophical discussions with people telling me that the spectroscopy is not operando, but the sample is operando. I say, yeah, sure, and the spectroscopy is not in situ, but the sample is in situ. In both cases, we are doing something which is a grammatic literature, but that you omit some words that you don't really need. So actually, in situ spectroscopy is what we say, but what we actually mean is a spectroscopy of a sample which is in situ, and then we say in situ spectroscopy. The same way that when we say operando spectroscopy, you say spectroscopy of a sample that is operando, and then we say operando spectroscopy. Now, these kind of things is what people from grammar call ellipses. Can anyone tell me what an ellipsis is? This is from grammar. Well, I didn't remember either. I remember the concept but not the word, and I have to ask. But the ellipsis is basically when you omit from a speech or writing a word or number of words that are superfluous or that you can understand from the context. That's why when we say spectroscopy of a sample that is in the site, you can say it in Latin, spectroscopy of an in situ sample, and ultimately you make the ellipsis and you say in situ spectroscopy. But it is not the spectroscopy, but the sample, the one which is in situ. And the same way, for operando, you say the spectroscopy of a catalyst that is working, you want to say it in Latin, which is more cool, then you say spectroscopy of an operando catalyst, and then basically what the ellipsis turns out into operando spectroscopy. Some people say, oh, you have to say in operando. No, you don't say in working, you don't say in making grammatical error, you say working, or you say in the site, but you cannot mix. So some people is contaminating the in and the in operando. Please don't do that. When I proposed the term operando, the first thing I did is to double check with a colleague who is full professor of Latin. And the message was very clear. It is operando, it's not in operando, because at lunchtime you are not in eating, you are eating. So it's the same, it's just present continuous tense in Latin, but no need for in. Okay, So that is something. Now, before going into that, we have to touch base about what is some details about the catalyst and some details about characterizing catalysts before we run into the operando thing. So let us walk, and tomorrow we will run. So when we characterize, we are making two kinds of characterization. One of them is mainly based on physical properties, physical probes, basically interaction of electromagnetic radiation with matter, and chemical probes. So for the characterization is always very important in catalysis research because it will give you information about what is happening there, just maybe for a quality control of your process. To understand how to make it better, you have to know what is happening. To characterize it at work, so you can do in situ studies, you can do operando, even real-time process control, process monitoring based on this real-time acquisition. But somehow you need to know before you go into in situ and into operando things. And typically, one technique may not bring the complete story. I tend to have a major focus on Raman spectroscopy, and of course everybody will have their bias. But you cannot rely on a single technique. You always need the backup of other techniques, and that will be instrumental to really build up the complete story. In the case of physical probes, when you characterize, you are getting all kinds of information, composition, structure, electronic, molecular level information, whatever. In the case of the chemical probes, it's more like surface information. We have already seen probes like pulsing CO, whatever. All these things are already like surface probes. And this is what I like to say NNR, this nature, number, and reactive profile. So it can tell you a lot of things about what is at the surface. And does it really matter? Well, yes, because there is also one challenge. When you make a characterization, the characterization will typically be bulk or surface sensitive, but it will typically not be only the outermost layer. The chemical probes will typically report about the outermost layer. So this is also very important, and we also have to keep in mind whether we are looking at the surface, at the bulk, or somewhere in between. And also single technique is not the answer, because you know the typical joke about a lot of people describing an elephant, and each person is looking from a different point, and this one will say, okay, this is like a spike, this is like a snake, this is like the log of a tree, whatever. So you need a complementary perspectives to really know that everybody who has a different description is actually describing the same reality, and that is very important. And this is probably one of the classical illustrations for this kind of concept. And remember what I said, that the spectroscopy typically reports about the bulk, not about the surface. Whether this is good or bad, it depends. What is really bad is that you are not aware of this. Once that you are aware of this, you use the information knowingly. For instance, you are making bulk characterization of a particle. For instance, this particle, planet Earth. There is no life on Earth. Come on, what do you say? There's no life on Earth. Oh yeah, I made bulk characterization, and this is what I saw. There is no life on Earth. Because these 6,000 plus kilometers of radius, with all these things without nothing living in there, the signal from the bulk overwhelms the signal from the surface. So you make a bulk characterization, there is no life. And there is evidence that there is life on Earth. We know that. So that is very important when you make a characterization, because it's not the same to be surface sensitive than bulk sensitive. And of course, if a particle is as big as that, the surface to volume ratio is so little, then the signal from the surface will be anecdotic. When you go nano, you trigger the surface to volume ratio, and then you will see the signal of the surface and the signal of the bulk, and then you can have a better perspective. But this is very important. Not only when you characterize, but also because during catalysis, the molecules, they really care about the surface. Molecules interact with the outermost layer of these particles, and they don't really care that much about the inside. I mean, indirectly they do care, because the properties of the surface is typically determined by the bulk, but the molecules interact with the surface, and if you want to connect the structure with the performance, it's important to know the bulk, but it is fundamental to know the surface, which is what is actually directly interacting with the particles. How do you characterize the matter? With a lot of radiations, or you can take the whole wavelength of radiations. Typically, benchtop conditions, like Sagar says, is close to the visible region from near infrared, infrared, visible until UV, which are things that we typically have in our laboratories, and which, fortunately, it is in energy range which is most informative to us. Like infrared is giving us a lot of molecular information, all the way to the visible, where you are getting electronic information. You can get major insight from your material. Raman is playing in between here because it can use many wavelengths, but in the end it is reporting also molecular information. You can use other wavelengths, higher energy, like X-ray diffraction, that will tell you about the distribution maybe of the nuclei, whether they have a regular pattern. Even you can use synchrotron-based application with X-ray to get a lot of more of information. That is much more specialized, or even other higher energy things. But most of the work, most of the things that you will have access on a daily basis, and most of the things where you really build up your knowledge is within the range of wavelengths of equipment that you can have on your laboratory. So this is also quite convenient. And I always like to be a little bit biblical, and you know that in the Genesis, in the Bible, it says, in the beginning there was light. And then God created the matter. And then when light met matter, there was spectroscopy. Well, that's not written in the Bible, but it is a consequence of the interaction between the light and the matter. So spectroscopy, like catalysis, actually spectroscopy has been long before catalysis. The only problem is that there was nobody reading. This is very similar to the summary that Sagar was telling us about all the techniques, but once that you specialize in using one or another technique, you will see details. So this kind of things is pretty available. One of the most common techniques, to me, this is not the main course, but it is a very important backup because I am more of a Raman person. This is infrared. Actually, I didn't say yesterday, but this is quite an honor and a little bit humbling to come to India to explain Raman. But I'll take it really as an honor and as a big responsibility. Because you will see that this is probably one of the very best techniques. And tomorrow I will describe in detail about Raman spectroscopy, the discovery of it, and key basic things that I think that are important. I'm not going to go into very detailed things about Raman fundamentals, group theory, things like that, but more on the practical side, which I think is of more value to better understand and take advantage of Raman and avoid being fooled by some artifacts that may be happening. Okay, in the case of infrared spectroscopy, we are dealing with a technique that we typically has an advantage because it is quite surface sensitive, and we can get a lot of surface information from the solid catalyst that we are looking at. In particular, for an oxide person like me, surface hydroxyls, surface oxygen bonds like this metal-oxygen double bond, these kind of things are very important. And also the evolution, the presence of adsorbed surface species during reaction or during a probe chemisorption of probe molecules. Infrared is quite good to monitor during reaction conditions, because things will change a lot and it will easily report about that. Infrared is very sensitive. So infrared will see everything. It will see the gas phase molecules, it will see the catalyst, it will see the adsorbed molecules, which is very good. But that means that you are making the experiment and there will be water in the environment, there will be CO2 in the environment, all these things will show up in the spectrum. So that is a problem and you have to get rid, and experimentally you have to make sure that in the path of your being it is as clean as possible from environmental CO2 and water, because they will give you a very strong signal. But the nice thing is that it is a very sensitive technique. So bearing in mind that, you can get a lot of information. The other thing is also very good when you use different kind of techniques to discriminate things. Like for instance, modulation excitation is a very specialized thing, because you will see a lot of, you're going to talk about modulation excitation, I'm going to talk about modulation excitation, because this is like a very versatile technique, very elegant, which is playing with a lot of things where you periodically change something. And then you can get a lot of information out of the things that change according to that perturbation and things that do not change. So we will go into detail, but just remember this modulation excitation spectroscopy is pretty much something that will become a key tool for operando studies in the future, and is already very extensively consolidated. Actually, in the latest operando conference in Switzerland 2 years ago, there was actually people saying that MES modulation excitation spectroscopy is the future of operando, and you will find the reason why. But that will not be tomorrow. Today, it will be later on. Okay, and then there is a lot of non-linear techniques and variations like some frequency generation that can be highly sensitive to surface. So out of infrared, you can do a lot of information, even very advanced surface science studies of materials. What do you see with infrared? Many things. What do you see if you are looking at oxides, at supported oxides? So one of the things that you first see is the presence of surface hydroxyl species. Like for instance, here you get all this vibration in the 36, 3700 wave number region that correspond to surface hydroxyl species. The surface of a material is typically covered by hydroxyls because this is the end of a material. Material is usually a 3D structure, which it will have a bulk structure, whatever it is. But in the end, the materials terminate. They have a surface. And the surface is a catastrophe for the material because this regular unit cell, which has been repeating ad infinitum, is no longer repeating ad infinitum because it breaks there, it ends. So the surface has to be stabilized. And the best way to stabilize is by absorbing environmental water, and this water will be absorbed in a dissociative manner, so you get hydroxyls all over the surface. So this is a very typical termination for many oxides. And this termination is actually having properties. Not all the hydroxyls are alike. Depending on their position, you can already tell whether they are more or less acidic. And also you can tell which kind of cation you are binding to. Like here, for instance, this is just a concept for alumina. Here you have the hydroxyl for alumina, but this is alumina with a little bit of sodium, with a little bit of silica on the surface. So you get the alumina infrared hydroxyl groups, but also some silanol, which is hydroxyls on silica. So they are different. So you can tell whether these hydroxyls are on silica or alumina on different kind of elements. And we also made a book, which is this one, this book of advanced catalyst characterization, which basically is more than 1,000 pages, and it has details on every technique for advanced characterization. So basically we got the leading people working on almost any kind of in situ and operando study, and they wrote a chapter. So we have one chapter that describes the technique, and then we have another one or two more chapters on case studies. So a different person describes case studies of that technique. And that is quite a very complementary, comprehensive. It's not pocket size, it's 1,000 pages, but it really goes through very many details of that. And this is from the chapter by Guido Busca on infrared. This is where we were talking here that you can see some silanol groups on the surface of alumina. The silica will have an infrared band like that. Even the simple thing as infrared spectrum of a catalyst is already telling you something. If you see, this is the surface of a silicon oxide, and you get essentially one peak. When you are looking at alumina, you saw many peaks. You know why is that? Well, silica is kind of a different material compared to others. Usually, most oxide surfaces, they have up to 7 hydroxyls per square nanometer, which physically is like a monolayer. I mean, in one monolayer, you can put up to 7 hydroxyls, so the whole surface is hydroxylated. But silica, depending on the silica, some silica is made at very high temperature, like fume silica at 1,000 plus degrees. It has a very high surface area, but it's hardly hydroxylated. It has like 1 hydroxyl per square nanometer. Now that means that you have a hydroxyl here, and the other hydroxyl is in the other class. So there is no interaction between these hydroxyls. And then you get quite a sharp infrared vibration for these hydroxyls. In the case of alumina, zirconia, titania, many other oxides, you have a hydroxyl here, and another one here, and another one here, so there is interactions, there are things. You can see many things showing that interaction between the hydroxyls. In the case of silica, you may have that. Eventually, you can get like geminal or vicinal ones, and that will result in a lower and lower frequency. This is not that common on silica, except on the more hydroxylated one, but this is increasingly common in the other oxides. And that's why you get a lot of bands, and not only a single band for the hydroxyl group. Here you have, for instance, surface hydroxyl groups on alumina. And you can see that you have a lot of bands. This is very complex, but that will be very informative, because these hydroxyl groups, they also have a function. When you are supporting on oxide, on silica, on alumina, on whatever, where do you think they bind to? what I have been talking about, hydroxyls. So they connect to the hydroxyls. Usually when you have in the surface a hydroxyl group, okay, we have a blackboard. So you have the surface, you have a hydroxyl over here, and eventually there is another hydroxyl over here, but if an oxide comes in, it connects with it. Like then you get vanadium, whatever, like connects to other hydroxyls. And basically the oxide that will support is titrating the hydroxyl groups. They stabilize. So if you want to make monolayers, supported oxides, they will typically connect to the hydroxyls at the surface of another support. You see that?
So it will act as anchoring sites.
Exactly, it's an anchoring site. That is the key word. So basically they will titrate them and they will react. So what means that if you are looking at a catalyst like chromium oxide on silica, this is the spectrum, infrared spectrum of bare silica. You have an intense hydroxyl group. If you put 1 or 3% of chromium, the intensity of these hydroxyl groups will decrease because some of these hydroxyl groups are taken by the chromium to make silicon-oxygen-chromium bonds. And then basically you can see how many of these surface hydroxyl groups are taken, what is the degree of coverage of chromium in this case on silica, or on the right side, okay, on silica is very easy because there's only one side, so you will see it linearly decrease until there is no more hydroxyl groups. Basically that will be the monolayer. So you cannot disperse anymore because there is no more anchoring site. In the case of alumina, the story will be similar, but doesn't look so elegant because you have many peaks. So the different peaks are being titrated. You will see that some sites will be titrated before than others, and then you can make a story about where does the chromium prefers to bind and so on. But in the end, the hydroxyl groups will be consumed. They will be taken. And so you can see that here they stopped at about 3 weight percent, and over here 9 weight percent because alumina has much more hydroxyl, so it has much higher capacity to disperse and to have a molecularly dispersed chromium oxide. You want to make a complete view and use different techniques. Like for instance, if you want to disperse titanium oxide on silica, you can do that. And if you make a look at the X-ray diffraction patterns, at the beginning silica will be amorphous. And then you put 8, 16, 32, 48 weight percent of titanium oxide on silica. And at the beginning you don't see that there is any titania. Also because X-ray diffraction cannot tell crystalline domains which are smaller than 4 nanometers that must be large enough to generate a diffraction pattern. Or if they're amorphous, there won't be a diffraction pattern. So in 16% you already see something, which is increasingly apparent as you increase, and here you have the reference for the titanium anatase. So basically you are starting to have a very incipient, very amorphous titanium oxide anatase. Now, you are adding this. If you make another complementary technique like X-ray photoelectron spectroscopy, XPS, you can look at how many titanium atoms you have at the surface. And basically what the XPS will see is close to the surface. So you are having more and more and more and more titanium on the surface. So the XPS will see more and more and more titanium. But there is a moment that to the XPS, there is no more titanium, because this titanium starts to grow up on top of itself. So you only see the titanium on top, but not the titanium behind. So somehow the titanium to silica ratio appears to level off as you increase titanium content, because that one is no longer apparent to the XPS because you are starting to make 3D structure of titanium. And that is basically corresponding to these values around 30 plus, 40, 40 plus, which is where you start to clearly see the diffraction pattern of X-ray diffraction. Now, where does this titania bind to? The titania is binding to the support, to the hydroxyl groups. So when you are adding titanium to this catalyst, what is happening is that you have hydroxyls from the silica, and you start adding titanium. So the infrared spectrum of this catalyst will tell you that there is less, and there is very little hydroxyl group left. So here, D is this one. You are at the monolayer coverage. Now, if you put more titanium, this is funny, because then you get more hydroxyl again. You know why? Try to say some answer. Don't say that I took a wrong sample in the spectrometer. It is the right sample. Imagine you are making a house, and you have a lot of bricks. So you're going to make a house here on this table. So you start to put bricks all over the table. There is a moment that the bricks are covering all the table, monolayer coverage. But now you're going to make a house. on this table. What happens? Will you see the table again? Yeah, because all these bricks will be here, and then again, you have the surface available. Okay, when you go above the monolayer, you no longer have a molecularly dispersed titania all over the silica. You don't have a monolayer of molecularly dispersed titania. Now this titania is gathering again. And when they gather again, the surface of the support is free again. So that is very interesting because you are going until you cover the support and then everything redistributes. You cannot stabilize so many titania species, then they aggregate. And when they aggregate, you are also losing the dispersion and you are getting the support. So this is clear? But it's a nice message. Sometimes you feel like, no, how come? I mean, if you are above monolayer, well, yeah, because now everything is no longer dispersed, but it's aggregated. It's like having a house before and after destroying the house. If you destroy the house, all the soil is covered, but before there was a nice garden around the house. So these kind of things. Okay, so this is a repeated slide or very similar. So basically, in a support, you have hydroxyls that you can nicely see with infrared. And the support can be anything. I write here titania, ceria, zirconia, alumina, silica, can be anything. And then you disperse oxides. And these oxides will also have vibrations. And these vibrations will happen, for instance, for supported vanadium, depending on the support. The vanadil mode will be at about 1000 plus wave number. And also the bridgings between the vanadium, the oxygen, and the cation of the support will have a vibration about 900 or whatever. And you will get these isolated species when you put a little bit, one here, one there, one there. If you increase the coverage, and of course, as you are adding it, you are consuming the surface hydroxyl groups. And when you are having this oxide, this oxo group will also show up. For instance, 1020 for vanadium, this is like 1008, which will be for molybdenum possibly, which is molybdenum oxygen double bond. But this is the kind of things that you will see with infrared. If you have more, these species will start to polymerize. They will get polymers because there's one vanadium there, but if they are nearby, there will be an interaction, they will be sharing oxygens, and then you will get bridging oxygens not only to the support, but among themselves. And this will be not VO support, but VOV, or molio, whatever is the cation that you have there. And they will have another vibration like 800 plus or whatever. Now, that's ideal. Supported oxides and infrared is fantastic and can see everything. It's the best technique in the world. I didn't say that. Okay. But many people may say, it's perfect. However, there's a problem with infrared. You can see hydroxyls, that's beautiful. You can see surface species, that's beautiful, but there's a cutoff. What is a cutoff? Well, infrared is very, very sensitive. If you have things that absorb a lot, it will saturate. And the problem is that the oxide supports tend to absorb quite a bit, especially below 900 wave number. And that is a problem. You see a cutoff here, it saturates. You see 1000 and below. 900 plus, you can still see something. Forget, this is zirconia, alumina, silica. That is a problem because most of the supported oxides characteristic vibrations will be at 1000 and below, and you cannot see. These oxide supports are killing you. And of course, then comes another technique, which is the best technique on Earth, Raman spectroscopy, that can tell you these kind of things. For instance, here you have infrared spectra in this region that is interesting for supported oxides, 700 to 1100. So alumina, very intense band, it's very difficult to see something there. Zirconia also has very bands there. Silica, a lot of bands there. Now, the Raman spectra of these oxides is different. It's very weak, and when you have sharp peaks, they are a relatively lower frequency and their intensity is not that high. Titania or zirconia, you will see bands below 700 wave number, but this region here, which is very important for the bridging oxygens and terminal oxygens, is still exposed. Some bending modes will not be visible here, like a vanadil bond will be like 1000, but then the bending like 200-300. That can be a problem on zirconia or titania, but you can see a lot of things. On silica, you get very weak bands. Gamma alumina is practically flat. There is hardly any signal. So you can see things very nicely. How nicely? Well, Raman spectroscopy, even when it is a weak effect with a weak signal, if you have like 1% vanadium oxide, molybdenum oxide on these materials, you will see the Raman bands of these supported oxides. This is unthinkable on infrared because with 99% of the support, this 1% of the supported oxide has a big problem going through the cutoff of the very strong adsorption. Back to the infrared. Infrared will report many things, maybe not below 1000. You can see this band at 1000, for instance, okay, you can see the vanadil or the molybdenil group. But anything below that will be a challenge, and mainly if the loading of the oxide catalyst is low. But above that frequency, it can really report very many things. For instance, I was telling you, depending on the position of the hydroxyl, you will see whether this is more or less acidic. But you can chemisorb probe molecules. You can chemisorb CO, you can chemisorb CO2, you can chemisorb pyridine, which pyridine is a very good probe for acidic sites, Brensted and Lewis. So depending on whether the pyridine binds, it will result on, sorry, that one was misplaced, but anyhow, I go back to that in a moment. Before going to the pyridine, just looking at the infrared position of the hydroxyl groups, you can tell how much of is, because the more Brensted acid the hydroxyl group is, the lower the frequency it is. So here you have like hydroxyls in a mordenite zeolite, in ultra-stable white zeolite, on amorphous silica. So you see how these zeolites have more acidity than the amorphous silica. Or a phosphated silica because of the phosphate group, or the niobium phosphate, which is acidic, or tungstated zirconia, which is acidic. You see how they go to lower frequency. So you can tell, okay, there is more Brensted acidity on these materials just by looking at the hydroxyls. And again, the other alternative is, even if you want to go in more detail, you can absorb pyridine, and the pyridine absorption will show different vibration modes depending on whether they sit on Lewis sites or Brensted sites. So it can tell you distribution of these sites. And depending on the sample, you will see like there is more Brensted than Lewis or more Lewis than Brensted. And then you can quantify how many sites, because you can quantify the chemical absorption of this pyridine, and also the population distribution of these Brensted and Lewis sites at the surface of these same materials I showed you before, only the hydroxyl groups like silica, CSM5, gamma alumina, etc. So that is very important. Now, for me, typically working with supported oxides, the main problem is that what I like, what I love, and what I really get the maximum amount of information of a supported oxide is in this region below 1000. Here you have Raman spectrum of the supported molybdenum oxide on alumina. This catalyst was like, there you have from 1 to 20%. You can see 1% at the bottom. You can see the things very nicely. 99% of the sample is alumina, not a problem. You can see these bands. Of course, the spectrum looks different. Raman, like infrared, is very sensitive to molecular changes. If the catalyst is under ambient conditions, it will be hydrated. Certainly in Madras, it will be hydrated in ambient conditions. But in Madrid, we have 30% humidity. It will also be hydrated. And over here, it will be much more hydrated, certainly. But when you hit the sample and you dehydrate, it will look like that. So the main difference, which is something that people did not really know, I'm talking about 20, 30 years, I'm old, 20, 30 years ago, that ambient conditions really have an effect on supported oxides, because supported molybdenum, vanadium, chromium, tungsten, all these elements which are very important for oxidation catalysis, they are sensitive to ambient moisture. They get hydrolyzed, they get solvated, they go totally hydrated. And then you see that they look different, and you can tell what is happening here. But the nice thing at this moment in time for today's talk is mainly that you can see supported oxides very nicely. Here, this is ambient hydrated. This is dehydrated. This Raman band at about 990, 997, up to 1000 is associated with the dispersed molybdenum oxide. As you increase the coverage, you can see this molybdenum oxide is polymerized, and then you get this additional band over here about the bridging oxygens, molybdenum, oxygen, molybdenum. So you can tell the polymerization. And also this stretching mode at about 1000. It also has a bending mode at about 200 that you see over there. Now, you can get a lot of information if you are making Raman spectra of these materials, particularly under dehydrated conditions. And I didn't say, but all the infrared spectra I showed you before are dehydrated. And all the infrared spectra I showed you are dehydrated because they have always made them dehydrated. Why? Because water is a problem, CO2 is a problem, so I make a vacuum treatment and we make it in situ in my cell without humidity, without CO2, without many things. So infrared has always been working with in situ dehydrated samples, to the point that actually people was not aware how important that was. But that was good. Getting rid of the water and CO2 was very nice, mainly water, because water has a dramatic effect on the structure of the materials. Okay, but this is basically something that we will see later on about Raman. This is what we see if we want to use infrared. The cutoff will allow you to see something. The humidity, yeah, okay, we see that there is a redshift at 1000 in dehydrated, 940 hydrated. Okay, you do see something, but you cannot see as much as this. Not only that, even in the molybdenil group, as you increase the coverage, as it goes from isolated to polymerized, you see that the frequency increases from 990, 997, all the way up to 1006. Even the position of the peak, it is also reporting you how polymerized this material is. So that's why I like Raman, because I'm looking at supported oxides. Infrared is very good, but it has this limitation with the cutoff. And today we'll talk about the techniques separately, but later on you will see that I make continuously connections with two kinds of techniques, infrared and UVBs, like Sagar said a moment ago, that I will be talking about these three techniques. It's kind of a trinity of spectroscopies. On the top we have Raman, and I have Raman at the top for one reason, because we see a very important complementary information from infrared. You will see tomorrow that Raman and infrared, while they are looking at vibrational modes, they look at very different kind of vibrations. One vibrations are active in Raman or stronger in Raman, and others are active or stronger in infrared. So you get some complementary information, which is also very important. Actually, you already knew that there was a complementarity, because the silica, the alumina, all these support give very strong bands, and Raman do not. So you already knew that while they are reporting molecular things, they are looking at different things. They have different sensitivities. The other technique which is important is UVBs. UVBs is important because we make Raman with visible light. And it's not the same to use a visible light, which is a laser, of a wavelength that has no particular interaction with your sample, than using a laser at a wavelength where your sample is absorbing. Because if your sample is absorbing that wavelength and you make a Raman with a laser of that wavelength, wow, there is resonance. And then you are triggering the signal. That is very nice. Oh, I didn't know. Then you get fooled, because sometimes you get something and the spectrum is dominated because a small component is absorbing. So, you know, there are effects. If you know, you can use them. If you don't know, you can be fooled. So this is very important. And these are like two complementary tools from infrared and from UVBs to Raman. Now, Raman, you already know, is at yesterday. It's because of Chandrasekhar Venkata Raman. It was originally not called Raman spectroscopy. Of course, Raman simply called it secondary radiation. And through the years, people said Raman spectroscopy, Raman effect. But it was called secondary radiation, and tomorrow we will see why they call it secondary radiation. Now, what can we say about Raman as key highlights? Well, it's extremely versatile because it's using visible light. That means that it can see through glass, through quartz, through sapphire, and that's ideal because in many reactors can be made of glass, quartz, sapphire, or you can have a reactor with a window of sapphire or whatever and look through it, and that will work. And that is extremely convenient because it allows you to investigate things under very noxious atmospheres, very extreme temperature, very extreme pressure, whatever, and you can do that. It is surface and it is bulk sensitive. Remember, planet Earth, there is no life on Earth. Don't be fooled by that. So you must remember that Raman is not only reporting the surface, but also the bulk, like most of the techniques. And that is very important because it is reporting about the two things. And the most important thing is that it is extremely sensitive to crystalline phases, nanocrystalline, below 3 nanometer. Less than 3 nanometer, you remember, cannot generate X-ray diffraction pattern, but that doesn't mean that you don't have a crystallite. And you can see with Raman very nicely nanocrystals of vanadium pentoxide, molybdenum trioxide, whatever, very nicely, even when they are not apparent to X-ray diffraction. You don't see it in X-ray diffraction because it cannot generate a diffraction pattern, not because they are not there. So Raman will report about these nano crystals below 3-4 nanometers, not much smaller because then you don't even have a crystal. Then you go to a few angstrom and then you're going into molecular things like just this molecularly dispersed vanadium oxide, and it will see that. The resolution, space and time resolution. Space resolution compared to infrared is much high because space resolution is optical resolution, and the optical resolution is typically half of the wavelength of the radiation you are using. Infrared is like you're dealing with 1,000 nanometers, so the spatial resolution will be like 500 nanometer. With visible light, it's 500 nanometer, 300 nanometer, so half that wavelength allows you to make higher spatial resolution. It's not an electron microscope, it's not whatever, but you can make some optical things, you can make some confocal studies within the material. So there are things where this optical spatial resolution is important. And okay, time resolution, well, that will depend because Raman is weak, so you need longer acquisition times. But then you have phenomena like surface enhanced Raman that multiplies by to 10,000 the Raman signal, where you can make very fast measurements. But there is another way to go around the time limitation, and one of them is actually the modulation excitation spectroscopy. This is another story that we will see in a few days, because this is going to be in crescendo. So the first days are easier and the other days are more fun. But well, I always enjoy, I hope you are enjoying the class also. And the other thing is that we can apply this to solid, aqueous solid interfaces. We can see what is happening at the interface of a solid, of the wet solid. You can see what is happening right there. That is very important in electrocatalysis, for instance. And of course, nothing is perfect. And in the case of Raman, the F word in Raman is fluorescence. And fluorescence is basically when light is coming out of the sample. Raman is very weak, and fluorescence can be like up to 10,000 times stronger than Raman. So if there is fluorescence, you cannot see anything. But there are ways to go around it, and that we will comment tomorrow. But okay, so these are like the general ideas about this. So why we like Raman? Because we can see the supported oxides very nicely. How they look like? Well, I made a drawing here. There you have another supported oxide, and again the same story. It's like before, but this is more complete now. I'm going from 0.7 on alumina, weight percent, molybdenum oxide on alumina. So, you can practice Spanish, by the way. Disperso here, this is Spanish. What does disperso mean in Spanish? Disperse, okay, you already speak Spanish, very good. Yeah, this is the dispersed molybdenum oxide. This is the molybdenyl bond, MO, at about 1,000. And as you increase the coverage, it will increasingly polymerize, so you get this MO bond that slightly shifts to higher frequencies because of the polymerization. And you also see the bridging oxygen, MO, which is over here. You get more and more and more because it is increasingly polymerized. Now that is happening up to 20 weight percent molybdenum oxide on alumina. You go to 25% and then you get new Raman bands which are sharper, which are stronger. These bands are no longer dispersed molybdenum. This is crystalline molybdenum trioxide. And the nice thing of it is that while the dispersed oxides are sensitive to ambient moisture, crystalline phases do not care. So that's very nice, because if you look at this same sample under ambient hydrated conditions, all these bands will change as we saw before into the hydrated one. But this, from the crystalline molybdena, will not change. So you have these crystalline molybdena bands over there, and then the other one. So you know that this one is crystalline and this one are dispersed, just by comparing hydrated with dehydrated. So you are getting a lot of information from things as simple as that. You can even look at what is happening with the supported oxide. Sometimes when you are making a dispersed oxide, you don't do like fancy things. You simply mix two powders, like alumina and molybdena, and you mix the powders and you grind them and you heat. And this is a very old paper. This is from a review from Gerhard Mestel, but this refers to a very old paper from the 70s or 80s, where you are looking at the Raman band of molybdena, which is over there, before and after calcination. And what happens before and after calcination is that this bulk crystalline molybdena spreads into dispersed molybdenum oxide. And Raman can see that. Even with the very old Raman system, very noisy, and you can see that. And the nice thing is that molybdena was spreading on alumina at 350. That is very interesting because the melting temperature of molybdena is about 600 degrees C. So why should it spread so soon? Well, because the surface free energy of dispersed oxides is much favorable than the free energy of a bulk thing. So there is a natural tendency to disperse. So it will spread and disperse on the surface. You can see those things with Raman. But of course, this is alumina support or silica support or whatever support. So a pure material will behave like that. What happens if you have additives or if you have impurities? In the end, there may be things, something very common, maybe calcium, sodium, potassium, they're everywhere. They could be in your sample. So what will happen down there? Will molybdenum spread directly and potassium, calcium, hello, how are you? Ignoring them, or will there be some kind of interaction? Well, that at the beginning may not be obvious, and that is interesting to know what is happening, and we will see what happens when there is another cation at the surface of this material. Basically, the complete view of the supportive oxide is like that. You can have isolated, polymerized, and nanocrystalline. Those that do not generate X-ray diffraction will be seen by Raman. The monolayer, sometimes people don't really envision it, but I like to, when I go to the south of Spain and you have all these olive trees, it's like these olive trees like that. It reminds me of a monolayer. You see a little bit of the support, and mainly you see the supported side. So each olive tree is like one of these supported vanadia, and the soil will be the alumina or the silica support of these materials. Another interesting thing with Raman is that sometimes the support and the supported phase react, and you get something like a mixed phase. Like for instance, vanadium and zirconia can make some vanadium zirconate, vanadium and ceria can make a cerium vanadate, whatever. And typically this is something that I always like from these drawings from Escher, because it really describes what an interface is. You know, these drawings from Escher, down here you have a fish, up there you have birds, and in between there's a moment that you don't know whether you have a fish, bird, or whatever. Well, that is the interface. And in catalysis, this interface where the birds are no longer birds but kind of fish, and the fish is no longer fish but kind of bird, which is very difficult to characterize, that is the phase doing the catalysis. And that is the phase that you have to characterize. So that is your headache. Because, oh, I see a bird, it's not working. I see a fish, it's not working. I see something between a bird and I don't know what it is. And that is the working phase. So this Escher drawing, I always like it because it really illustrates very nicely the challenge of understanding catalysis, because the active phase is never a very crystalline, very well-defined phase. Now, the other question, impurities. What happens with impurities or with additives, sodium, potassium, calcium? When you disperse molybdenum oxide on silica, this is what you get. Here you have a catalyst, which is molybdenum oxide on silica, and dehydrated. So this 1000 is the MO, this oxo group of the supported molybdenum oxide. The supported molybdenum oxide will have like this. And that will be about 1000 more or less. So this is what you see here. Now, if there was some cesium, potassium, or sodium, you see something else. What do you think I see here? These new bands that are not apparent before. Crystals, exactly, alkali molybdate, cesium molybdate, potassium molybdate, sodium molybdate, or on the right, it was dramatic, it was calcium molybdate, very, very strong. These other bands that you see here, this is part of the silica. Silica has like weak bands here, and so this is silica. But these new things is from the sodium, potassium, cesium molybdate, and here you have calcium molybdate, it's quite sharp. And we are dealing with little loadings, and you can get already important information even about the role of impurities. And another important information is sometimes I don't really know what is what, but then you can use isotopes. For supported oxides, for hydroxyls, you can replace oxygen 16 by 18, you can replace hydrogen by deuterium, and then the vibration will be essentially the same, but something very important changes in the vibration when you are replacing oxygen 16 by 18 or hydrogen by deuterium. What important thing is changing? What important thing is changing? Exactly. The mass is changing, and then the reduced mass is changing. And that goes with a very close relationship with the frequency, because the bond and the energy of the vibration will be the same. But if one of the elements becomes heavier, the frequency at which it is vibration becomes lower. It's like when you hear something vibrating, you know this is heavier light because of the frequency of the vibration. The heavier it is, the lower the frequency. Same thing happens here. There's a shift in the frequency. There's a red shift. Red always means lower and blue higher. So there's a red shift. Frequency goes to lower frequency. Like CH will be vibrating at about 3000 with the same strength. If this hydrogen goes to the deuterium, which is twice as heavy, the frequency change is dramatic, goes from 3000 to 2100. oxygen 16 to 18, the mass increase is more moderate, but you do see a decrease in the frequency. These vibrational modes is molecular information. These kind of effects you can see in Raman, but you can see in infrared. So this is also like very complementary information that you can get about what is happening. So here, for instance, you can see like surface, when the surface is changing the surface hydroxyls between hydrogen and deuterium, you will see a red shift to lower frequency. And of course, the other peaks is the band from the silica, like here, here, and here. Now, you remember something that may be confusing, and during these days, you will see that signs the Raman spectra, the frequency is growing to the right, sometimes the frequency is growing to the left, sometimes you see like this, but sometimes you see the other thing on the other side. And I know this is kind of confusing. And so you will have to always look at the numbers to see if the spectrum is going in this direction or in that direction. And the reason for that is something that we will comment tomorrow. Usually people draw it like that because as you increase the frequency, you increase the energy. And typically, IUPAC is always telling you to represent things with increasing energy, like this. But in the case of Raman, what you are measuring is energy taken by the sample to the laser. And so basically, what you are measuring here is that the photon that arrives to you has been stolen an increasing amount of energy. So that's why they plot it on the other way. It's a way of making headaches. I grew up with this way. Now, even the Journal of Raman Spectroscopy is asking you to do it like that. You never know. Every journal you make is, no, you have to make it in the other way. And each journal is publisher has a different policy, whatever. So you have to live with that. Okay. The same thing that you make with oxygen exchange, you can also make with the hydrogen deuterium exchange. And again, you can see how there is a frequency shift. For instance, here, so you can see how this is associated with hydroxyl group in the surface of the silica, and how the other bands of the silica are not affected. Basically, these vibrations are associated to siloxane bridges of CO, oxygen, silicon rings, and they are there. They don't care about replacing hydrogen by deuterium. But this one is associated with surface hydroxyls, and that one changes. Because that one, there is OH or OD, and then there is a change, but the other ones are not affected. So these kinds of things can help you either on Raman or in infrared. Also, you can also look at the vibrations and also make the questions, what is the actual structure? Because sometimes people is talking about molybdenum like this, and sometimes they talk about molybdenum like that. So basically, 2, 3, 4, 5, 6, 2, 4, 5, 6. This hexavalent molybdenum in any case. So it's molybdenum 6 plus. In this case, you will have one vibration, and here you have two. In this case, things are very simple. In this case, you can have symmetric, asymmetric, whatever, all these things that you can see on the screen. So, for instance, in molybdenum, you have this kind of vibration at 300, at 900, 68, and 983, symmetric, antisymmetric, and bending modes. If it were like that, it would only have one. Depending on the case, you see this and you see that. So depends on the coverage, depends on the support. You may have monoxo or dioxo. And one nice thing that you will find out is that when you compare Raman and infrared, for instance, in this case, if this vibration is stronger in Raman, this is weaker in Raman. But for infrared, it's vice versa. This one will be stronger in infrared and strong in Raman. So if you see like this in Raman and you see like this in infrared, you know you are dealing with dioxo. If you see a given frequency like this one in Raman and exactly the same frequency in infrared, it's because it is just a single band. Sometimes over here, for instance, maybe one of the modes is so weak that you don't see it, you only see one, but Raman will see one, infrared will see the other. So if there is a difference between Raman and infrared, they will be dioxo. And if they're identical, they will be monooxo. And of course, there are systems like rhenium, which is 3-oxo. So it has one leg and 3-oxo group because rhenium is heptavalent, it's rhenium 7 plus. And of course, if you make isotopic exchange, the possibilities is like none of them is replaced, one of them is oxygen 18. So in addition to the very many peaks that you get for a trioxo, if you get oxygen exchange, that will be crazy. So the most simple case is you make oxygen exchange on a monooxo species. Then basically you have the vanadil oxygen 16 or vanadil oxygen 18. And in this case, they are just flowing through vapor of water, which is H2O with O18. So little by little, the water is replacing the oxygen system by oxygen 18. And basically what happens is that you are losing the oxygen system and you are getting the oxygen 18. So it's a very elegant experiment, which very nicely illustrates how it's a single oxo group. One is being disappearing and the other is appearing. So basically you replace one by the other. Chromium is a dioxo species. Then things are not so clean and one is not replaced by the other, because then you can get both of them like 16, 16, 18, 18, 18. So you have a plethora of peaks and things can go more complex. Then this is already telling you, okay, this is dioxo species. And if you do that with rhenium, you get crazy, because you have all these very many possibilities of 1, 2, or 3 of the oxo groups replaced by oxygen 18. So you begin from something which is very nice to something that is a very good headache. But this is telling you that this is a trioxo if you make a detailed analysis of the system. And isotopic leveling can also give you a lot of information during operando reactions, but that will be in future chapters, not today. 5 minutes, how do we go? Okay, fine, yeah. I don't. Well, I'm looking about other surface species. Maybe this is a good moment, because then we can settle things and then we take it from here tomorrow. But then give us for questions for local people and also for the people at the other side of internet. And who is willing to make questions and comments or whatever? Please speak up, sorry.
Yeah, for varying percentages from 1 to 10%, are the acquisition conditions are always same, like
Yes, in those.
frequency and the resolution? Because is it like when we optimize to find it out, were they all the same conditions or
This spectra with a very similar frequency was somewhere over here, like that, for instance, with increasing loadings. Okay, all these spectra were made with the same acquisition conditions. So you don't really change much. I mean, this, I made it many years ago. I'm actually scared to count how many years, but acquisition time in that time to each of these spectra, maybe it was like 20 minutes. Now you can make it in 1 minute or seconds. But the acquisition time, it was essentially the same for all of them. And basically what you can see is like on the lowest one, it is a little bit more noisy. So you see that the signal to noise ratio is a little bit worse, but all of them have the same acquisition. And this one is worse because there was much less amount of molybdenum, so much less things, but still you can see that the molybdenil vibration is very clearly defined. The evolution of Raman is amazing, because when I started, the first Raman system I was using, probably you saw it at Lehigh, or maybe the laser was like a half this table. And behind it, you have like a huge water circuit to refrigerate. And then the power plug was one of these things that do not approach because you die by electric shock. It was like, I don't know. And the laser was amazing. You put a paper and the paper started. And now the detector was also like a different style. Now the new Raman systems, the whole Raman system, not only the laser is on the table, is much smaller than those lasers. The acquisition time is much faster. The laser power on the sample is like 3 milliwatts. And 3 milliwatts for a laser is a lot, or is not that much? Well, before we got these screens, we got beamers, and then we were using laser pointers. Laser pointer is like a 1, 2, 3, 4 milliwatts. So basically now the laser that you are putting in a sample is very little, because we are optimizing things, because you also have a microscope objective to better concentrate the signal. So right now the measurement is extremely much more sensitive, much more simple. So these spectra were 20 minutes each, and another 20 minutes aligning. Now in 20 minutes you get all the samples analyzed, and several times. More questions? Yes?
So you mentioned like the molybdenum oxides from the different kinds, for example, monoxo, dioxo, and polymerization, right? But the monoxo, dioxo, when it is in the disposed state, it can interact with the moisture.
Yes,
But the polymerized one will not interact with the moisture.
it will. Yeah. Both isolated ones and polymerized ones. Like for instance, if you have some polymerized. Am I inside the screen? Yes. Okay. Yeah. I mean, I owe to my audience. I have internet followers. I'm now an influencer this week, so I have to make sure that they see me in internet. Okay. So also when you have polymerized things like that, either polymers or isolated entities, when the water is coming by, the water will interact with them, the water molecule will come by, it will break that, so that the water molecule in the end, if you get a water molecule here, and this hydrogen will go with this and make a hydroxyl, and this other hydroxyl will connect here to make an OH. So in the end, this guy will have vanadil and a hydroxyl, and there is another molecule and it will break it, and it will break it, and it will be totally solvated. But over here it will also break this, and it break this. So in the end, everything will be solvated. However, if you get a vanadium pentoxide, that one will not really care. So isolated and polymerized species are moisture sensitive. They will interact with ambient moisture, they will be hydrolyzed, they will be dissolved, but usually the crystallites, molybdenum, vanadium, whatever, they don't really care.
But crystalline also will have the CO bonds.
This kind of structure, well, depends, because this structure is a structure that happens because of the spreading. Like a molybdenum oxide it will have a bulk structure. It can be alpha or beta molybdenum, whatever. But these two crystalline structures is a structure where you only have molybdenum and oxygen. Now, when it disperses, you have molybdenum, oxygen, and silicon, or aluminum, or cerium, or whatever is down there. So it's something different. It's no longer molybdenum. It is molecularly dispersed molybdenum oxide. Because now it's not only this element, but a new element, the cation of the support. So it is molybdenum. We call it molybdenum silica, molybdenum titania. But when we say molybdenum, we don't mean molybdenum. I mean, we don't mean alpha molybdenum or beta molybdenum. We say molybdenum. Even you put the formulation, say, no, my catalyst is MO03 on silica. Maybe you may want to say something like MOOX on silica. Usually, we tend to say that, because if you say that, it may mean that people, when they mean that, they say like, oh, I put nano MO3, and then you are creating like new nomenclature, and IUPAC people gets very happy. But so usually I like to say MOX on silica, because yeah, it's something like that. It can be like this, or can be polymerized. So even, but it's not the oxide. And actually this is what it makes it different, because typically catalysis is associated to the oxygen atoms. Which one? It could be the oxo, or could be that one. And actually the bridging oxygen is much more accountable for much of the catalytic performance, because it's the one that is changing the most, because if you have molybdenum on silica, on alumina, on ceria, the performance is very, very different. And actually this is because typically this is the site where the reaction is occurring. And that is what it makes it special. It's no longer molybdenum, or yes it is, but it is not as it used to be. It's molybdenum interfaced with something else. And that was make the catalyst special. Always the interface is making you different, is making you special.
Thank you very much for the detailed answer.
Mm-hmm.
So I have a couple of questions. Like for example, you mentioned that we can use pyridine is a good probe molecule.
Sorry? Pyridine, yes.
It's a very good probe molecule to probe the Lewis acidic sites versus the advanced acidic sites.
For instance.
So can you please comment on using the ammonia as a probe molecule?
Ammonia as a probe molecule is also a sensitive one. It will also absorb on Lewis and on breasted site, and you will get different ammonia or ammonium vibrations. The challenges for ammonia, it depends on your sample. We will talk about this in, I don't know, 2-3 days, one example, which is selective catalytic reduction of NO with ammonia. And in this case, we will be looking at the infrared Raman bands of absorbed ammonia. But the problem with absorbed ammonia is that ammonia may absorb like NH3 and like NH4+. So that will be like Lewis acid site and like Brensted acid site. The problem of this Brensted is that it will absorb at 1600 and 1200. So, well, this is awful. You can tell I don't use a blackboard regularly, okay. So the 1600 is pretty much like water. So if you want to have something, you get a strong interference from molecular water absorbed at the surface. And then 1200 will be okay. So you will see the Brensted at the 1200, which is weaker than that one, but free of interference. And for the other one, it's about 1450 or something like that. So you can see these two bands as well. But usually people with pyridine is making more quantitative studies and analysis because they don't have interference from water or moisture. But both of them are good, and there are other probe molecules.
Okay, we can also do it like at a high temperature so that we can remove the moisture.
You can do a high temperature, yes. And typically, one of the things that is also made, because of this point of the temperature is a very good one, is like you can make an infrared spectra of a chemisort pyridine or ammonia and increase the temperature. And then you will see that the Brensted or the Lewis are leaving before or after. So you can see this Brensted side is stronger than the other one, because even if I increase the temperature, it's still holding it, and the other one is losing it. So you can also tell the evolution of the pyridine Brensted Lewis against the temperature, because this will tell you how strongly they bind. So then you get additional information from there. Thank you. No questions from the left side of the audience? Or from the other side of internet? Okay.
So I'll ask another question. So you mentioned that in the SiO2 silica. So
In?
for the silica,
Yes.
you get a clear peak, right? I mean the single peak compared to the alumina.
For the hydroxyl group, you mean? Yes.
When you treat it at a higher temperature. But again, when you are doing the experiments, again you are exposing to the environment, then the water molecule can come and get absorbed. That can get
Hydrated. Yes, this is something I will be talking, I believe, tomorrow, because that is very important, and is the importance of ambient moisture, how the surface gets hydrated. Actually, this is a beautiful work. You probably know Gautam Deo from Kanpur. He made amazing, fantastic work about the nature and the role of ambient moisture on supported oxides. So tomorrow I will show these Gautam's results, but basically what is happening is that we always talk about in situ dehydrated. So the samples are at 100, 200 degrees C in dry air. Now, ambient conditions, all these things get hydroxylated, hydrated, solvated. It's not only that you get that, it's that in the end everything gets dissolved into water. So everything decouples from the surface, decouples from the surface, gets totally solvated and goes into the liquid phase. And what kind of a structure do you have under ambient conditions? Liquid phase chemistry. So if you go for an analytical chemistry book and you look at what phase of molybdenum, vanadium, chromium, whatever you will have, you will see that it depends on the concentration and on the pH. Well, exactly the same thing happens there. And Gautam got amazing Raman spectra of all the samples of vanadium, molybdenum, and different oxides on different supports. Depending on the support, depending on the coverage, you change the concentration and the pH. Perfectly matches. Now you heat, the water evaporates, and then what happens? The oxides go back to the support, and they get, again, molecularly dispersed, because everything is dry. So this is a completely reversible change. More questions?
So in some of the slides, that quantification you told, right? The quantifying the Lewis acidic sites and the Francis acidic sites. So when we do the quantification of this kind of sites, so what are the things we need to take care of during the experiments? I mean, your suggestions.
Well, basically, I mean, for quantification in infrared, you're typically working on transmission infrared. Infrared, you can work on diffuse reflectance, or you can work in transmission infrared. Transmission infrared is more tricky because you have to make a very thin wafer to put it into a kind of an envelope inside the cell. And making this wafer is not something for the people with very anxious, because they break easily. It's very difficult to make. But the nice thing is that in such a case, when you have the infrared wafer, you have a wafer and inside the cell, and then you are exposing to the whatever, and then you get the molecules absorbing over here and within the porosity of it. And in the end, you are making the infrared spectrum. And then the Beer-Lambert law applies. So whatever is being absorbed will depend on the path, will depend on the concentration, and will depend on the extinction coefficient of the sample. So you must always know what is the thickness of your sample. You can calculate by density, okay, in the end you can calculate that. And you can normalize the intensity of these pyridine bands based on that. And usually the infrared beam is not like a nano beam, it's something a bit bigger. So it will average a zone. So if your wafer is representative enough, whatever is going through should be representative of it. And then you can get the intensity just by doing the absorption of these infrared bands and compare. The relative values will always be reliable because you get Brensted to Lewis, how it is changing. But the absolute value should also be right if you normalize to the thickness of your sample. And then you can monitor the evolution with temperature, with composition, with whatever.